My name is Markus Nemitz, and I would like to talk about collectively revolutionizing robot swarms from a sensing perspective. As some of you know, I work in a collaboration with the University of Michigan, and that is how I really see myself and the academics I work with. We're a collective that tries together to work on swarm robotics from very new perspectives. Swarm robotics can be introduced probably in the best fashion by talking about natural swarms. Ants, bees, termites, fish, birds, they are all collectives where the individual has a simple behavior. But many of these agents that interact locally with one another lead to complex or emergent behaviors. These emergent behaviors are very interesting because they oftentimes are robust and flexible. For instance, if you have a collective of 1,000 ants and accidentally 100 of them die, then you still have many of them left to continue the task at hand. These tasks, they range from aggregation to finding food sources or defending the collective from intruders. In swarm robotics, we're interested in extracting information from natural swarms and apply them to robot swarms for the very same reason. When I started my PhD 3 years ago, I found that there was not a single swarm robotic system that was easily to manufacture and easy to extend. So I built the hoverbot system, which is shown in the figure in this slide. On the right side, we can see the magnet levitation table, which is basically an air hockey table with permanent magnets embedded into its surface. And then on the left side, we have the actual robot, the hoverbot. The hoverbot is a printed circuit board which has on its bottom side 5 planar coils embedded. A simple transistor circuit allows to energize these coils, and if now a hoverbot levitates on the table, it can interact with its coils with the permanent magnets, what then causes two-dimensional locomotion. The nice thing is that the hoverbot costs only $10 in large quantities and is very easy to manufacture. Hoverbot's arguably most interesting feature is its Hall effect sensor in the center. As we will see, it can be used for the detection of many different events. So on this slide, we see 3 different magnetic field measurements. Each measurement shows the magnetic field over time for a specific event. The first one shows the successful movement of a hoverbot from one position to the other. The second graph shows what happens if a robot collides with an object. And the third one shows what happens if a robot accidentally rotates by 45 degrees. We then collected many of these data sets and built actual classifiers, one classifier for each category, and then programmed the microcontroller with these 3 classifiers. In total, we pay 20 cents for the Hall effect sensor, and we used 20% of the microcontroller's computational power to detect 3 measurements. This is an example of how the classifier works. The classifier is now programmed in the microcontroller, and it tests a new measurement time series against the classifier. Since they're both very similar, it calls this a match, and the microcontroller knows that it just moved successfully a step. This is an example where the classifier detects an unsuccessful movement and it does not result in a match. If you look at previous swarm robotic systems, the majority of systems only measure up to 2 measurements with a single sensor. There are only a few exceptions, including the Hall effect sensor of our hoverbot. Thank you for your attention. I plan on continuing my research in swarm robotic systems next fall at Harvard University in the George Whitesides group, where I recently accepted a postdoctoral fellowship upon completion of my PhD next summer.